So it is a privilege to introduce my supervisor, Professor Dr. Venkatesh sir, for this session. So Professor Gudipadu Venkatesh is an assistant professor in the Department of Mechanical Engineering at the National Institute of Technology, so NIT Warangal, India. He holds a Master of Technology, MTech and a PhD in Mechanical and Industrial Engineering from the Indian Institute of Technology, IIT Roorkee. With over 10 years of experience in teaching and research, Professor Venkatesh's primary research interests include the application of microwaves in manufacturing processes, nano finishing of advanced materials using hybrid abrasive flow machining, HAFM, and surface engineering. He has successfully supervised 2 PhD students with 4 others currently pursuing their doctoral research under his guidance. Professor Venkatesh sir has completed one funded research project and is currently working on another. He has authored more than 45 research papers in reputed journals and conferences and holds a patent for his work. In addition, he serves on the editorial boards of 5 academic journals and has delivered around 30 guest lectures on various topics related to his field of expertise. Through his teaching and research contributions, Professor Venkatesh continues to make a valuable impact in the field of mechanical engineering. So now I am introducing Sir Venkatesh sir for this session. Please welcome sir for this session. Please bring up ours.
My voice is clear. So now we are in the 4th day of the course. So I hope everyone enjoying the sessions with some laboratory arrangements, live demonstrations, etc. So coming to today's session, so our course is majorly on nanomaterials. So we have learned several basic things about nanomaterials, etc. Now we will see some applications. So where do we use finishing? So nano level finishing in healthcare applications, finishing of implants, etc. So the major outlines of the presentation will be discussing on conventional finishing processes and limitations and advantages of conventional finishing, introduction to abrasive flow finishing process, and several things about surface finishing challenges of AM components and future directions, some case studies, etc. So we all know what are finishing processes, right? So we have conventional finishing and non-conventional finishing processes, etc. So in conventional finishing processes such as grinding, honing and lapping process, so whenever you finish the materials, so there are some constraints with respect to the geometry of the material. Like you can finish only a flat workpiece or a cylindrical internal surface and the external cylinders using cylindrical grinder, and sometimes some concave surfaces using some processes like grinding, lapping, honing, etc. So in these processes we use fine abrasive particles which acts as a tool material. So these fine abrasive particles will remove the workpiece material in a form of a chips. So these chips are in microns and nano level. So the material is removed in micro level and nano level. So these processes are not a complete machining processes. These are finishing processes. Means the material removal will be very low. Okay? Material removal will be very low in milligrams. So there are certain processes where we get cross hatch pattern. So when we have a rotary and as well as translatory motion, so then there is a chance of getting some cross hatch pattern, and we have some applications for getting the cross hatch pattern etc. in the finishing. And there are some difficult to finish materials, mainly non-metals. So non-metals such as some, let us say some ceramics which are brittle in nature. So it is difficult to machine using a conventional processes because the tool is directly in touch, directly in contact with the workpiece. So whenever the tool is directly in contact with the workpiece, there will be a lot of machining forces generated, okay, frictional forces, and due to that load, there is a chance of breakage in the material and the finishing is difficult. So these are some of the limitations. So one is the geometry. If the geometry is complex, how do we finish it? And the second is, if you want to finish a non-metal, or if you want to finish up to nano level, Armstrong level, then we need some advanced processes. And why high precision is essential in healthcare applications, in implants, etc. Why high precision is important? So precision ensures components meet exact design specifications, enhancing functionality and reliability. So basically surface quality matters in several aspects like micro electromechanical systems. Surface functionality and reliability will matters in aerospace components, automotive components, biomedical fields, medical implant industries. So everywhere, like wherever the components are subjected to friction, when you are assembling 2 or 3 components which are subjected to friction, then there is a chance of wear. So our target is to reduce this wear. So wear, so we need high-end finishing. We need nano level finishing in order to achieve that. And there are some aesthetic appearance purpose. So we do required finishing. And coming to challenges, surface finish challenges, the components, the complex components which are manufactured using additive manufacturing. You can see several implants here, several complex implants, orthopedic, dental implants, and several implants are 3D printed, okay, are 3D printed. We will also see the lab today, okay, 3D printing, metal 3D printing lab, and as well as our lab, okay, so abrasive finishing, and we'll also plan a Siemens visit as well, okay, this is not done for your batch, okay, so that also will plan. So in order to address these issues, okay, so what is our problem? Our problem is if the components are very complex in nature, so how to finish them and how to deburr them, right, and how to radius them, such a complex geometry, we need certain advanced process, not like grinding and honing lapping, okay. Grinding, honing, lapping can be possible only for the simple geometry. And when we see the capabilities of several finishing processes, finishing in micro level, nano level, and even in Armstrong level. So there are processes such as grinding, honing, lapping, abrasive flow machining, magnetic abrasive finishing, magnetic float polishing, magnetorheological finishing, and some hybrid processes. So in all these processes, we see what are the capabilities of these processes. You can see the RA value in nanometer. So this is the capability of grinding, this is the capability of honing, and we can observe the capability of abrasive flow machining. Okay. So our target is to reach the nano level finishing of the components, okay, of the complex components. So I am working on one particular method. The name of the method is abrasive flow machining. So this method, this setup will achieve nano level finishing of the complex geometries. So what are the general challenges in the modern metalworking industries? Development in material science. Probably you have seen several cases, several conditions, like how the material science is advancing and how the new alloys and new materials coming in the research field and as well as in the industry. So how to target them and how to make a possible solution for achieving the required specifications. So one solution is abrasive flow machining. So abrasive flow machining is a process developed during 1960s. So it's not a new. It is developed in 1960 by Extrude Horn Corporation in USA, and it got patented by the company. So that particular technique, and this particular technique comes under the advanced machining process and as well as advanced finishing process. And this is capable to deburr, radius, polish and remove recast layer of the finished component, which are finished to difficult components, and this is used to finish the complex internal passages of the components, etc. So here I would like to show the principle of abrasive flow machining. Okay, so the major principle and material removal rate mechanism. So in this particular process, there are three major components. So one is machine, second is the flexible tool, and the third is the fixture, okay, where we fix the workpiece. So the machine here we are using is two-way acting hydraulic setup. Can you see the image? So we are using a two-way acting vertically mounted hydraulic setup. So using this setup we can control pressure, okay, we can control flow volume, flow rate, right, of the hydraulic pressure, etc. Okay, how do we apply? And we have a semi-solid tool which is flexible in nature, which is a kind of like the slime, kids who are playing with the slime, right? So we know how the slime behaves. So this kind of material is mixed with the sharp edge abrasive particles, and that is pumped in between the workpiece. So let us say here we have a workpiece, a cylindrical workpiece, and this semi-solid media is pumped to and fro in between, like flowing in between the target surface. Like, so this is our target surface. Okay, when you pump this media under high pressure, okay, which pass on the target surface, then the abrasives present in the media will flow on the work surface, hitting the asperities at certain force which is generated by the extrusion pressure applied. So due to that abrasion will take place. So due to that abrasion will take place, and the abrasive particles present in the media will remove the material in microchips and nano chips. So this process, the initial roughness itself is in microns. Means if you want to finish any component, the initial roughness itself we maintain in microns and we reach to nano level. Okay, it's a sophisticated process. It's not like the rough is converted to smooth. Already the taken workpiece is in smooth. We are going to nano and Armstrong. Okay, for several applications, like for medical applications, aerospace, defense applications, where we require high level finishing. There we use. The workpiece dimensions you are saying. So we need to prepare a fixture based on our dimensions. Okay. So once I'll show the video, you will get some idea. Yeah. So this is a technique I'm talking about. So the yellow color shows the abrasive media and the blue color shows the workpiece. And we have a, like while pumping, these abrasives are with a certain axial force, they are, okay, abrasion is taking place. You can see here, so this is the workpiece and non-cylindrical hole, internal finishing and as well as external finishing is done with abrasive flow machining. So like this is a bit difficult to use a simple process, okay. So in this video, like you can see the semi-solid media. So they are showing the abrasive particles. So we can use silicon carbide abrasives, aluminum carbide, okay, aluminum oxide and boron carbide, etc. can be used. You can see the media how it looks like after mixing with the viscoelastic polymer, okay. So we use viscoelastic polymer gel for mixing the abrasive media. So this is a flexible tool I am talking about. So this flexible tool is pumped in between the work surface. So whereas in the video you can see they are using a one-way abrasive flow machining. They are pumping that semi-solid media with a high pressure and the media is coming out from the workpiece. Say this is the workpiece. These are the manifolds used in our automobiles. So this media is coming out from them. While coming out, actually it is doing that radius, okay, radiusing, it is doing the deburring, it is doing the required correction. So we need to control that. So you can see the complex micro holes are removed and multiple holes can be removed, and this is a tool. So this is a flexible tool we are talking about. So some automobile components, some complex geometry, okay. So after finishing they are removing the media, okay. So the media property is very important here. I will explain after the video. So like you can see these kind of components which are casted will have several issues after casting. So we require post-processing of these components, okay. Because to radius them, to deburr them, to finish as per the requirements. So we do a lot of finishing techniques required. And 3D printed components. So using 3D printing we can print several complex geometries. So using 3D printing, like 3D printed components can be super finished. And aerospace industry, several components can be finished up to nano level using this particular process. Finishing of a cross holes. A straight hole we can use some process, some simple process, but finishing of a cross hole, finishing of a blind hole. So finishing of extrusion dies which are complex in nature, like you can see the channels. So how do we finish the channels? So aluminum extrusion dies with different shapes. So finishing of non-metals as well. So ceramics finishing and polishing of several opticals, bent pipes, okay, and metallurgical molds which are very hard with complex geometry. So mold polishing, even finishing of screw threads, glass mold polishing. So heat runner inside hot polishing. Yeah. So like I think you got some idea about the process we are discussing. So we are using a novel flexible tool for finishing the complex geometries. So this tool, which is flexible in nature, will have a viscoelastic properties. So it will carry viscoelastic properties. So what is this viscoelastic? So there is a lot of study on viscosity and also elasticity behavior of the polymer which we are using in the study. For example, like when you brush your teeth with a toothpaste, so toothpaste is viscosity is different and it is having different behavior, like it's kind of a viscoelastic behavior, it's a toothpaste gel. If you add some salt particles in a toothpaste and brush your teeth, okay, you are applying certain pressure and you are brushing your teeth. So the result is your teeth will shine because the paste is carrying the salt particles successfully and you are reaching the target finish. So the finish is our finishing the teeth. So you are reaching and you are applying certain pressure and then brushing. Okay. Similarly, if you add some sand particles or abrasive particles and brush your teeth, what happens? Blood will come out, right? Because of the nature of material you are adding. So if you add abrasives are hard in nature and they are having sharp cutting edges, the blood will come. Okay, but however, you are using a media which carries your tool, right? Similarly, like when you add sand in a glass of water, so the sand will settle down. Means you cannot pump water and abrasive here. If you add sand in a oil, then it will not settle down because it depends upon the viscosity. It depends upon the viscosity of the medium you are using. So whatever the media you choose, whatever the gel you choose, it should have certain viscoelastic nature. Okay, some people are using rubber milk, the natural rubber milk getting from the trees. They are taking that rubber milk and then adding abrasive particles in it and allowing it to become viscous, and then they are pumping that for finishing. So there is lot of study on the type of media used in abrasive flow machining and its properties. So we need to study the thermal stability of the media used and the behavior of the media and as well as the temperature properties. So when we are pumping the media to and fro, so what is the difference in the temperature, right? Because we are doing abrasion process. So what is the difference in the temperature? And there are studies on TGA analysis, thermogrammetric analysis of the media. So to see if there is any endothermic and exothermic reaction taking place during the process. Okay, so here the principle explains you in abrasive flow machining media quickly abrades the peaks of the rough microsurface at the first, after which the valleys become slightly abraded as the peaks flatten into plots. Eventually a smooth and uniform profile is produced with no trace of the original surface. So this is what happening during the process. So these abrasives hitting the target surface and then some small microchips are removed from the target surface and the process will continue. The third important component in the process is tooling, as the sir asked, like how the tooling is designed and for different geometry, for different workpieces, how the finishing is possible. So the major role of the tooling is it holds the workpiece and as well as it guides the media so that the media will pass on the target surface. So these two things we need to keep in mind while preparing the tooling or the fixture, right? So when we prepare a fixture, we need to keep in mind two things. One is a proper seat for your workpiece. You can see here, this workpiece is different and this workpiece is different, this workpiece is different, and there is some complex fixture here. So for your designed workpiece, for your desired geometry, you need to first prepare a fixture. That fixture will allows the workpiece to sit and as well as to guide the media so that the media will pass on the target surface. So these two things. So see the applications in turbine engine parts before and after, in the medical implants, finishing, and whatever the video we have seen. So we have seen all these kind of applications. And to have some clarity on the finishing of bent pipes and the complex geometries and the flexibility of the media. So some this is a mixture of some mixing oil, and in the laboratory you will see the media preparation and as well as the fixture preparation, how the fixture is prepared, and then how the finishing will take place using this flexible media. So you can see here, this is the workpiece. So how the media is pumped to and fro, and then how the finishing is taking place. Yeah. So whatever the setup we developed based on our project, okay, based on our requirements in the lab. So this is the design model. So initially we thought of designing the abrasive flow machining or vertically acting abrasive flow machining. So this is the design model and this is the fabricated model, and you can see the fixture. So this is the fixture. So if you disassemble the fixture, you will see the seat for the workpiece and as well as the guidance of the media, so that the media is flowing to and fro on the target surface. Okay, so we are targeting to finish the internal geometry of this workpiece. Okay, we are targeting to finish the internal geometry of the workpiece, and how it can be done and what are the parameters that are playing a role and how the finishing takes place, etc. So this video will shows you the to and fro action, what we expected. So these are the medium cylinders, these blue color medium cylinders, and two acting hydraulic cylinders are there. So we fill the flexible media inside one cylinder and will pump the flexible media to and fro, passing through the target surface, so in between the fixture. So this is a simple AFM. We will see some advancements, how people worked on different aspects, etc. So this is a to and fro action. Yeah. Now we understand the principle, right? So what is the principle and what are the major components? As I said, three major components. One is the setup, second is the flexible media, and the third is fixture. So we have designed, the literature says the influencing parameters of these three major components. So when we take the machine settings, the major machine, extrusion pressure will play an important role. So what is the pressure you are applying on your abrasive media, and based on that pressure your axial force will vary. So the abrasive particle which is carrying, the media is carrying an abrasive particle, will have certain axial force with respect to the applied extrusion pressure. So that by varying the pressure, actually we have influence on the result. Second is the number of cycles and how many cycles, like when we pump the media from one cylinder to another cylinder, we calculate it as one cycle. Okay, so when the media is pumped from bottom cylinder to down cylinder and then from down to bottom again, so we calculate it as one cycle. If you increase the number of cycles, the surface finish rate will vary. Okay, if you increase the number of cycles, the surface finish will increase, and also the material removal also will increase. So this is also one of the important parameters. Flow volume and its speed. So this also can be controlled by using the machine. So if you know the cylinder diameter, etc., and the volume, etc., we can be calculated and we can have the control on the speed as well. Coming to abrasive media. So abrasive media viscosity plays an important role. So what is the viscosity, whether it is a low viscosity media or high viscosity media, and how to measure the viscosity of the media, and media rheology. So to know more detail on the viscosity like shear rate, instantaneous viscosity while pumping the media. So what is the viscosity of the media after finishing, before finishing, and instantaneous viscosity of the media when you are pumping, when it is flowing through the surface. So what is the viscosity, etc. In detail can be studied about the media rheology. Next, abrasive type, size and concentration. This is the type of the particle you are choosing and the size of the particle and the concentration. So you can choose either abrasive as a silicon carbide or any other abrasive particle, and size and concentration also matters. So if the abrasive size increases, then your material removal increases, whereas your surface finish deteriorate. Okay, if you use coarse grains. If you use fine grains, the surface finish will improve better, whereas MRR will be low. So there is an impact on abrasive size and concentration. Concentration means, so the percentage of abrasives you are mixing with the media, that polymer gel. Say if you are mixing 50% of polymer gel with 50% of abrasives. So what is the impact? If 40% of abrasives mixed with 60% of polymer gel, so what is the impact? So like that there are studies to know the impact of abrasive concentration. Coming to tooling and as well as the workpiece, restricting passage length and area. So while designing a fixture, how you are restricting your passage to have a better control on the velocity and the pressure of the media flowing towards the target surface, and the type of workpiece you are choosing. So what is the hardness of the workpiece? So depending upon the type of the workpiece, you need to choose the abrasive type. Okay, you need to choose the abrasive type, size and concentration also. Right? If you are using very hard material like cast alloy and nickel based alloy, etc., then accordingly you need to choose the abrasive type. So this is the media preparation. So we will show a small demonstration also in the evening. So the abrasive particles mixed with the mixing oil, we use naphthenic based oil here, and the polymer gel, and how it becomes a flexible media, a semi-solid media, and how it can be tested, okay, and how it can be used for functioning, okay, for processing, for finishing, etc. And we use different grades of silicon carbide particles like 120 size, 80, 60, even 180 size, etc. So under scanning electron microscope, so we have identified the size of the particle, right? Size of the particle we are choosing, and also the shape of the particle we can identify. So while pumping the media, so we observed before and after finishing of the sample under the defined pressure, and we also working on a 3D printed components which are having applications in medical, okay, mainly fracture plates used in fixing the ankles. So these fracture plates are planned to finish using abrasive flow machining. So we are studying before finishing and after finishing of the fracture plates. So these are the 3D printed components. So as a part of lab, we will also show the 3D printed lab, 3D printing lab, and as well as our finishing lab. So you will get some idea like what we are working on. So some basic study we have done on a design fracture plate. So you can see here, so this is a design fracture plate and this is a original fracture plate, and we have not used our machine here because our machine was under fabrication during the study. So we used a machine which is available in CMTI Bangalore, so abrasive flow machining. So they pumped the media to and fro on a sample, and these are the parameters we used in the study, like the abrasive grid size used and the viscosity, and you can see the density, abrasive percentage, pressure, etc. varied. And we observed the finishing of the samples by varying the number of cycles and as well as by varying the extrusion pressure, and we could achieve some kind of mirror finish before and after abrasive flow machining. And also you can see, so these are the conventional machining marks. You can see the deep tool marks which are found by a conventional machining, and the deep feed marks or the deep tool marks are removed by abrasive flow machining, right? So this is not a final achievement, okay? We need to work on improving better. We need a mirror finish, mirror reflection, and also we need to take more complex geometries for finishing. Yeah. So these are some of the results. These are some of the results at different cycles, 50 cycles, 150 cycles, and 350 cycles, 450 cycles. So as I said, one cycle equal to like when we pump from to and fro action, right? So here we observe that 450 cycles we are getting certain finish. Okay, so let us say RA value from 1 micron to say some as per the scale here. So the finishing is RA value is not exactly, yeah, you can see here. So the maximum peak here is say some 10 micron, and here you can see some 0.1 etc., right, 0.1, 0.2. But this is not sufficient, and also we observe that it is taking more time. Okay, 450 cycles is huge, so we need to spend a lot of time for finishing. So these are some of the observations on the fracture plate, and some applications of this particular process, especially finishing the recast layer which are formed by EDM process, and finishing the 3D implants, 3D printing implants, 3D printing components. Nowadays is a very important application. So in aerospace industries also, people are looking for a novel process for finishing the 3D implants. In the recent ISRO projects brochure has released, I think some might have seen. So there also there is one of the project requirement where they are looking for a process which can finish aerospace components which are printed by using 3D printing. Okay. In that applications we can see how the abrasive flow machining and other processes can be utilized. Yeah. So the literature says that 80% of the cost of the final finishing component comparatively manual. So 80% of the cost will be saved. Like if you use a mechanical process comparatively manual. So the process is easy to operate, and it is used to reach the high tolerance. It can be used for high-end finishing, and it can finish inaccessible areas. So there are several advantages, and the major disadvantage is the process is low, means slow. So it suffers with low finishing rate, and a lot of processing time is increased, which will implies the increase in the manufacturing cost of the overall component. Okay? Since the process is slow, and also the material remold rate is very low. It is in milligrams, so the material remold rate is very low. So in order to address these limitations, there is a lot of research started, okay, to hybridize the process. So we will discuss few. So to hybridize the process, many people have tried different techniques, different approaches to hybridize the process. So what is hybridization? So combining two or more techniques in order to achieve the efficiency of to improve the efficiency of the process. So how the abrasive flow machining is hybridized, and what are the results, and what are the what are the major achievements of this hybrid AFM, etc. So we will be discussing. So there are some magnetic field based abrasive finishing, and there are ultrasonic assisted abrasive finishing. There are some rotary based abrasive finishing, and drill bit guided, centrifugal guided, and electrochemical abrasive finishing, etc. Right? So the people who are in mechanical background, I have seen some 2 to 3 or 4 participants specifically from the mechanical, and of course it's a combo of different people. So we understand how this hybridization help and what kind of hybridization they are doing and how they are addressing those limitations. So hybrid AFM types I would like to show again. So magnetic based abrasive finishing. So it's again further divided into 2 types: magnetic assisted abrasive flow, magnetorheological abrasive flow, and people tried chemical based abrasive finishing. So electrochemical abrasive flow finishing, centrifugal based abrasive flow finishing. So here centrifugal assisted abrasive finishing and spiral assisted abrasive finishing, rotary based, ultrasonic based, etc. Yeah. So there are several types, and every hybrid variant is one PhD work. Okay. I worked in this particular area where I used ultrasonic based, right? So using ultrasonic vibrations, how the finishing is improved further and how I address the limitations of conventional abrasive flow machining. Let us see one of the hybrid variant. So magnetic assisted abrasive flow machining. So here also the principle is same. So here you can see the abrasive media and the two-way acting hydraulic setup and the workpiece tooling, and they are using a cylindrical bush as the workpiece. And when we pump the media to and fro, okay, when you are pumping the media to and fro, so the media will flow on the target surface at certain extrusion pressure. And we are looking into the media viscosity, media flow volume, media flow rate, and we are looking into the constraint created. Everything is taken care. So apart from that, so there is a modification in the setup if you observe. There is a modification in the setup if you observe. So the modification is, so electromagnets are arranged. Okay, magnetic field is arranged around the tooling. Okay, when you vary the magnetic field density, okay, when you vary the current, so how the media is reacting under that magnetic field. So they tried using magnetic workpieces, magnetic materials, and also non-magnetic materials as the workpieces. And they added some iron particles, small iron carbon particles in the media, and they prepared a different media and they pumped. So when the magnetic field is on, they observed that these iron particles mixed with silicon carbide are having more impact in the tooling zone, because the tooling zone is under the control of magnetic field. So the result is there is more active abrasive grain density, means the abrasives are participating more when the magnetic field is applied than without magnetic field application. So they studied how the finishing rate improved and how the material removal improved, so when the magnetic field is on. They also studied by varying the current, by varying the other parameters related to magnetic field, how the impact on finishing, etc. So they studied. But they did not study more on the magnetic viscosity of the media and what is happening inside to the rheology of the media. So they studied mechanically like how the finishing and how the material removal takes place when you are pumping the media to and fro. So these are some of the same images like before finishing and after finishing. So how the surface has been finished. So this image is taken from the paper. So like you cannot see the smooth finish. Yeah. As I said, they did not study more on the rheology of the abrasive media, like finding out the magnetic viscosity of the media. In the next year, in the 2004, Another researcher has developed the same kind of setup, but he concentrated more on magnetorheological properties of the media. In the previous case, in the year 2002, they have conducted that particular study and they got PhD. Okay, and this 2004, so all these are done in IITs only mostly. So they work more on magnetorheological abrasive flow machine. So what is the difference? So they studied more on the rheology of the media. I will show you that. So when you are pumping the media to and fro, as I said, they added iron carbon particles inside the media, and we also have the silicon carbide particles in the media. When the magnetic field is applied, then these carbon iron particles are forming like a chain. This chain formation is possible when you apply magnetic field around the tooling. And what is the purpose of this chain formation? They explain in a schematic. So when the silicon carbide particle is surrounded with a carbon iron particle chain, when the magnetic field is applied, then not only the abrasive particle will have more interaction to the asperity, but also the abrasive particle will have more axial force because of the surrounded iron carbon particle. So the hitting of the abrasive tendency has been increased. Okay, so these are the asperities on the workpiece. So due to this carbon iron particle chain, the abrasive hitting tendency has been increased. Okay, and also there is more active participation of abrasive particles when the magnetic field is applied. So people are working on synthesis of abrasive particles. Okay, people are working on the type and shape of the particle and the iron carbon particle size, okay, to have a better control on the process. So this process, this magnetorheological finishing process, there is one project, ongoing project, in even ARCI people are working on finishing an optical surface. Okay, so they prepared for a bulletproof opticals. Okay, they want Armstrong level finishing. So for that actually they are developing a magnetorheological finishing process where they mix this media along with the iron carbon particles, and the chemistry is also involved to study the synthesis of the particles, and several aspects they are working. Not only the mechanical abrasion, but also there is more to study about the rheology of the media, so which will have lot of physics and as well as the chemistry as well, to have a better control on the while finishing. So their target is to finish their components which they are using for like safety purpose. Okay, like as I said, the opticals, bulletproof opticals which they wear, okay, when they required. So how to finish them? Okay, so another advancement in hybrid AFM is centrifugal force abrasive flow machining. So this author tried to control the process by introducing centrifugal force. So how he achieved? So he took the fixture design as a challenging in this particular process. Okay, so he made a patent also on the fixture. I will show the image of the fixture. Yeah, so this is a simple fixture and some addition in the fixure with a rotating attachment and as well as with the centrifugal rod. So they fixed a centrifugal rod and they created a fixture with a rotary mechanism. So this centrifugal rod is inserted in a cylindrical bush. So you can see here. So this is a centrifugal rod and this is a fixture, and they rotated this centrifugal rod and the centrifugal force is generated. So this centrifugal rod is inserted in a cylindrical bush. So our target is to finish the cylindrical geometry in this particular process. So how they achieved, you can see here. So they worked on finishing of cylindrical bush that particular workpiece by varying the size of the rod, by varying the shape of the rod. They observed how the constraint of the media is created and how the finishing is improved, and also they observed that when the rod is rotated at different RPMs, what is the impact of abrasive flow machining, okay, what is the impact of surface finish and material removal rate, okay, during that rotation process. So this is one of the hybrid variant. So they worked on several materials and they claim that this particular process is giving better result compared to simple abrasive flow machining. Yeah. So another author has tried rotary abrasive flow machining. So in this particular process, so the workpiece fixture is rotated, means the workpiece is inserted in a fixture and that fixture is rotated when you are pumping the abrasive media. Okay. So you can see here they are using a one-way AFM, so one-way hydraulic action, and the other side they are using a spring loaded and a sliding disc. So once you release the hydraulic setup pressure, the back pressure, the spring will do its action. Means we have a two-way action, but the design is different. Okay, so the other side we are not using a hydraulic setup, we are using a spring loaded sliding disc, and they inserted a spindle and this spindle is connected to a motor. So when they rotated the spindle is also connected with the workpiece. So they rotated a spindle, so the workpiece fixture is also rotated, and they pumped the media, and they observed that when you are rotating the fixture which is inserted merged in the media, and also we are pumping the media, so they observed some different result. So that the result is that the abrasives are having more grain density compared to simple AFM, and also they are covering the circumference of the sample, okay, and they got some uniform finishing because of the rotation of the work surface compared to simple AFM. Because in simple AFM, when you are pumping the media, we observe that several abrasive particles are inactive. Means they simply roll and slide. They simply roll and slide without cutting. So those abrasive particles we consider it as inactive abrasive particles. They simply roll and slide. They don't do that particular job. But our job is to make them more active by giving certain hybridization, like by rotating it or by vibrating it or by applying magnetic field, okay, or by generating centrifugal force. So there are several concepts, several things done by several people. Next, author tried drill bit guided abrasive flow machining. Okay, so in the previous case we have seen the workpiece is connected to a spindle and the spindle is rotated, right? But in this case, the author inserted a drill bit rod inside the workpiece and then he controlled the finishing, and he named this particular process as drill bit guided abrasive flow machining. I will tell you what is the major outcome of this process, okay? So the drill bit is inserted in a cylindrical bush and they are pumping the media to and fro. Okay, so due to the helical fluid path of the drill bit, so the reciprocating axial flow is possible and as well as scooping flow is possible because we are pumping the media. So media is reciprocating and that it is flowing on the work surface and in between there is a drill bit. So due to the helical fluid behavior of the drill bit, there is more possible action is flowing of the media in a fluid path, axial flow and the scooping flow. So because of these two different types of flows, they observed the material removal rate is more compared to simple AFM process. So because of the drill bit nature, okay, because of the geometry of the drill bit, so they observed more interaction. So the author tried to increase the abrasive grain density, means the active participation of abrasives on the work surface, because the major limitation is the simple FM process is very slow, okay, low finishing rate. So they wanted to increase the finishing rate. So they tried in different ways. So one tried using centrifugal force, one author tried using magnetic field, one author tried using rotary, and one author using drill bit guided, okay. So he did not rotate a drill bit, only by the nature of the drill bit, okay, by the design of the drill bit, how it is impacting on the work surface. So next, rotary abrasive flow machining, like it's similar to the previous process, but he explored in a different way, like he has taken two-way acting abrasive flow machining, and he rotated the entire fixture. In the previous case, the workpiece is inside the media, right? So here the fixture is rotated. The fixture is rotated and the workpiece is inside the fixture, and the media is flowing on the work surface. So what happens here? So he observed that the abrasive media flow inside the work surface, how it varies by varying the RPM. Okay, so the flow of the abrasive media is controlled by rotating the workpiece. Okay, and he also worked on the helical rotation of the work region, and how this helical motion will helps in finishing, and also how it helps in improving the finishing rate in this particular process. So he has studied on several workpieces, and several results were published, and several results are compared with simple FM process. Yeah, so you can observe here some images which shows the abrasive scratches in helical path, and also that flow behavior, which explains that rotary behavior of the workpiece, and also the result shows about the change in RA value by varying the abrasive media and also the extrusion pressure. So we can see the trend curves of the results, how the result is increasing and then further decreasing. So another author tried spiral flow assisted abrasive flow machining. So as I said, in drill bit guided assisted, the drill bit is not rotated, right? So whereas in spiral flow, they rotated drill bit. So they rotated drill bit, and then they tried on different workpieces, and they observed that at lower RPMs it is giving a better result, the scooping action, and at higher RPMs that scooping flow is missing, only it acts as a simple rod. So they recommended at lower RPMs this spiral flow assisted will give better result compared to simple drill bit guided abrasive flow machining. And ultrasonic flow polishing. So this is the first method introduced as a hybrid method, okay, which is combined with AFM process. Okay, so the ultrasonic flow polishing is a combination of AFM plus USM. So we all know ultrasonic machining process, and abrasive flow machining also we have seen now. So when they combine these two, so what is the result? So they worked on a finishing of a blind hole. So their workpiece is a blind hole, and they targeted to finish that particular blind hole. So when they are pumping the media to and fro, so one way they are applying the extrusion pressure, and the other way the tool is designed in such a way that the media is coming out from the tool, and the ultrasonic tool is vibrated at high frequency. So the abrasive particles present in the media are excited due to this high frequency, and a small gap is maintained between the work surface and the ultrasonic tool, and due to that high frequency vibrations, the abrasive particles are acting more active, means are more active compared to simple FM. So due to that, the abrasives are removing the work material on the work surface. So this particular process is majorly used for finishing the blind hole compared to the through holes. So next, whatever the area I worked, so ultrasonic assisted abrasive flow machining. So like in the previous case, they vibrated a media and they got some better result. And in our case, we vibrated a workpiece externally, okay. So we vibrated workpiece externally and we studied how the finishing is improved and how the vibration assistance helped in finishing and how we reached nano level finishing and the process mechanism as well. So with vibration and without vibration, we conducted some case studies. So we worked on some application oriented materials, etc. And so those things we'll discuss few here, few important things. So this is the setup I would like to show. In ultrasonic assisted abrasive, we used a horizontal setup, horizontal AFM setup. It is not a vertical AFM, it's a horizontal AFM. The reason is, while using this vibrations to the workpiece, so we had a better opportunity to vibrate the workpiece in horizontal AFM compared to vertical AFM. So the horizontal AFM is designed. So here we can see the hydraulic cylinders and the medium cylinders and the tooling and the piezo actuator which is vibrating the workpiece, and it is connected to amplifier, DC offset and then computer. So we can vary the frequency and also we can vary the amplitude of the workpiece while abrasive flow machining is on. Means while pumping the media to and fro, parallelly we can vibrate the workpiece, and in which direction we are vibrating the workpiece, that is important. So we are vibrating the workpiece perpendicular to the media flow direction, okay. So we are vibrating the workpiece perpendicular to the media flow direction, and we also tried parallel to the media flow direction. So what is the effect, what is the result, and how it is better process compared to simple AFM process, those things we have discussed. I would like to show some schematics where with vibration and without vibration, so what could be the possible result, so why the finishing is better. So in the figure A, if you observe the workpiece and the abrasive particles traveling in a media, so the surface, this is the target surface which we need to finish, and this is a media flow direction, and this is the abrasive particles A. So when we are vibrating the workpiece externally, we observe that the abrasives are hitting at an angle theta. So the abrasives are traveling unidirectional when you are vibrating at high frequency, and also the abrasive force, the particle force and the resultant velocity is varying because of the additional vibrations given to the workpiece. Because when you vibrate at high frequency, which is perpendicular to the media flow direction, the radial force is increasing. So the radial force of the abrasive particle is increasing, and however the axial force of the abrasive particle is controlled by extrusion pressure. So this is a horizontal AFM process, we could able to control the extrusion pressure as well. So now when we vibrate the workpiece at a sinusoidal cycle, okay, at a sinusoidal cycle, so we have a rising off and receding off cycle in a sinusoidal ultrasonic vibration. So in this rising off and receding off, the vibration which is inverse of time, at different time intervals, we have the enhancement of asperities, and then in the rising enhancement and then receding. So because of that, we observed some intermittent cutting action will take place, and we also observed that some abrasive particles are becoming active when there is change in the amplitude, with additional vibrations. So this is a side view of the workpiece. So this side view schematic is shown to show that the abrasive protrusions are everywhere in the circumference of the surface because of the vibration in the sinusoidal cycle, and the result is we could achieve a smooth surface finish and as well as a uniform surface finish. So this is one schematic I would like to show, like when the vibrations are given to the workpiece, like how the particle will be having a better resultant velocity compared to simple airflow. In the second schematic, the illustration is like when you give vibration and as well as at a defined amplitude, the chances of becoming inactive to active particle will increase, because at a rising of the asperities are advancing, because we are converting the electrical signal to mechanical action. So we are using a piezo actuator. For me, the mechanical action is important. I wanted to vibrate my workpiece at a defined amplitude, at a defined frequency. So when you advance the asperities, there is a chance of the inactive particle becoming active because of that advancement. And when you continue the process, then there is a chance of cutting action and also intermittent cutting. So because of the continuous sinusoidal cycle, and finally the result is the finished surface, okay, the finished nano level surface. And what is our job is, the major important is like whether the process is rapid or not. So that is what important for us, okay. So with finishing and without finishing, with vibration and without vibration, whether the process is rapid or not. Yeah. So this is another image which shows the tendency of abrasive heating in ultrasonic abrasive flow machining at a different T, at different time intervals of a sinusoidal cycle, how the abrasive is heating the asperity and how the cutting action is taking place and how the chips are removed and how the smooth finish is achieved. And at different events some proof is also taken, like using atomic force microscopy and as well as optical microscope. So how the sharp edge asperities were cut. So this is a nano chip cutting, you can see this small chip is cut here. So already the sample is a finished sample. We are working on to cut a microchip, a nano chip, okay, and we are working on how to have a controlled process for cutting nano level, okay, for cutting a nano level finish. Yeah, we tried vibrating in axial direction parallel to the media flow direction. So when you are pumping the media to and fro, we in the previous case I have shown when you apply vibrations radially to the media flow direction, and now when we apply in an axial direction, so then how the impact is, okay, at the rising of and at the receding of, how the impact is. And like based on the case study, we observed that when we vibrate radially, the result is better than when we vibrate the workpiece axially, because we are perpendicularly vibrating to the media flow direction, then there is more interaction of the abrasive particle, more radial force than the vibration in axial direction. So that's what one observation. And coming to simulation and also some case study, so we have chosen bevel gear as a workpiece. So this is a bevel gear. So we all know bevel gears are used to transmit motion for a perpendicular shafts. So bevel gear design is somewhat difficult, some intricate compared to simple gears, and we can also try helical bevel gears, right? So as of now in the case study, like we have taken a bevel gear as a workpiece and the fixture is designed accordingly. As I said, the fixture is important and the fixture design will play a role in finishing. So the fixture is designed in such a way that the media will pass on every tooth on the designed bevel gear, and also we targeted to finish a uniform finish of the gear which we are finishing. So why we studied simulation means we wanted to know the media flow behavior when we vibrate the workpiece, okay. we wanted to know how the media behavior is changing when we are vibrating the workpiece. So we observed that the media flow velocity distribution is changing compared to simple AFM, and media flow pressure distribution is changing, and also the velocity vectors of the media which are flowing on the workpiece are straight in simple AFM process, whereas the velocity vectors are perpendicular when we vibrate the workpiece. So that is one observation. And the temperature. So we observe that the temperature is slightly increased when we vibrate the workpiece. With vibration and without vibration, there is a slight increase in the temperature of the media. So these are some of the things in simulation we observed. And some image you can see here where the boring marks, the tool feed marks which are done conventional machining processes are finished by using abrasive finishing process. Okay. So this is before finishing and after finishing. We can observe a glaze surface, glaze after finishing, and this is what I am talking about. When we apply vibration in the simulation process, we observe the velocity vectors traveling at an angle theta, and in the simple AFM the velocity vectors are traveling at an straight. Okay, so the user defined function simulation is taking place. So we used ANSYS Fluent in order to simulate the process. So where we used vibration, sinusoidal vibration, and as well as the media flow parallelly and also perpendicularly. So these are some morphology of the surfaces, and you can also see the abrasive marks and the finishing on a bevel gear. And these are some images where you can see the real fixture. Okay, so in the previous case I have shown the simulation fixture. So this is a fixture and this is a machine, horizontal acting machine, and how I am importing the vibrations and the workpiece, and the schematic explaining the mechanism. Okay, so when we vibrate, so what kind of result we are going to get? Okay, in a sinusoidal cycle, so what kind of result we are going to get? Okay, this paper we published in Machine Tools and Manufacture journal. Okay, one of the prestigious journal. So Machine Tools and Manufacture in elsewhere, I think the impact factor is more than 10. Okay, we published this work because at that time no one published in ultrasonic assisted AFM. So there is a process, ultrasonic flow polishing, but there is no process so far who vibrated the workpiece externally while finishing. Okay, so this is one result. So in the paper, one of the result we claim is to show the process is rapid. So that is important because we are working to overcome the result, the limitation. So the table shows the experimental conditions used in UAFM process and AFM process. So in UAFM, the two important parameters we added, so that is frequency and amplitude. So frequency and amplitude are the two introduced parameters in UAFM, whereas in AFM these two are zero. Okay, we are not vibrating and also we are not giving any amplitude. And coming to other parameters, extrusion pressure, processing time were kept constant. Okay, extrusion pressure, processing time, media flow rate, abrasive size, concentration, viscosity, etc. Everything kept constant, only we wanted to study how UAFM will affect and how AFM will affect. So the result shows here on the y-axis surface finish improvement and on the x-axis processing time. Processing time is nothing but number of cycles. So we convert the number of cycles in time. Okay. So and the second result shows the material removal in milligrams. We are not calculating any rate. So we wanted to see before and after how much material is removed. So we observe here the black color shows simple AFM, whereas the red color shows UAFM. So we observe one important observation here. At 5 minutes of processing time, we could reach 30% improvement in surface finish when we use simple AFM, and at 15 minutes also we could reach only 55% improvement on the surface finish, whereas at 5 minutes itself we could reach nearly 65% improvement in UFM. Means within 5 minutes we could achieve more than what we achieved in 15 minutes in simple UFM process, more than that. It means that the process is rapid, and also it is increasing the finishing rate compared to simple UFM. The similar kind of result we observed in the material removal as well. So what we could not achieve in 20 minutes also, we are achieving in simple UAFM in within 5 minutes. So that is one important observation we climbed. What is? Here, this is to show the slope, and how the curve, etc. So, if you see the schematic the SEM image and the optical microscope, we observe the deep feed marks and the rough surface on the bevel gear, and slowly the smooth surface, like after 5 minutes, 10 minutes, the smooth surface and the reduced feed marks, reduced abrasive scratches were observed on a bevel gear. And as I said, people working on abrasive finishing, which are published in Additive Manufacturing Journal, so they choose a copper tube, one of the case study, a copper tube which is 3D printed component, were studying for different finishing processes. So this is as built 3D printed components. So they evaluated longitudinal and lateral surface finish as built, and they choose the setup. This is a big setup in IIT Tirupati they have. So they use this particular setup for finishing that 3D printed copper tube, and I would like to show the result. So they use this particular media, the galactominin abrasive media. So galactominin is one of the chemicals they use in food processing. So the chewing gum and some candies which are having that viscoelastic nature, so they are using that particular constituents, glycerol solution, and that constituents for preparing this media, and they got patent also in this. Okay, so which are flexible in nature, which are viscoelastic in nature. So they are working more detailed, like the people who are in the chemistry background and the physics background, for them this will be the major important area, whatever based on today's session. If you can work more on constituents, you can work more on chemistry of that behavior of the media, its viscoelastic nature, synthesis of the abrasive particle, right? What kind of constants we are using, etc. More. But as a mechanical engineer, I will more concentrate on finishing and MRR, like how this media is thermally stable. Okay, what is its shear viscosity? Okay, and how it helps me in finishing, etc. That is my concentration. But someone can work on this area, like how to prepare a novel media with all the properties and the functionalities which we require. So these are some of the input parameters like which I discussed, and these are some of the calculations, how the material removal is calculated, and the abrasive finishing rate in percentage is calculated, etc. And this is a SEM morphology of the media prepared in the case study, where we observe the abrasive particles and the base polymer. Okay, the base polymer, the galactominin polymer, and the abrasive sharp edges, the polymer media and the abrasive sharp edges you can see, and like the used media, like after finishing you can see the wear on the abrasive particle, and as well as some micro chipping and also some blunt cutting edges, right? So before finishing, this is the media behavior. So you can see the separate polymer and abrasives. You can also observe that the polymer carrying these abrasives successfully, and after finishing you can see some blunt surface on the abrasive and the micro chipping and cutting edges, blunt cutting edges, etc. like after finishing. And after finishing, of course, you can also see the metal powder. So the metal powder is also mixed along with the media. Yeah. So as I said, the TGA analysis, thermogrammetric analysis, FTIR analysis. I think in the Professor Harinath sir has explained about several characterization techniques, right? So for a non-metals, for a polymers, if you want to study in detail about its behavior, its main constants, and time versus temperature, how it is behaving, so that is one kind of study you can do. So in this particular process, whatever we are discussing today, we'll have some laboratory session as well along with the 3D printing lab. So people who are interested can work more on the media behavior. Okay, so majorly thinking about what kind of requirements we need, what kind of behavior is in detail about that. Okay, but we study more on finishing and mechanical things, but the participants may discuss more on the chemical and the chemistry and physics behind the media. Okay, so the TGA analysis and FTIR analysis to know the main constants, and coming to the results. So they were looking after the number of cycles only. So at the number of cycles, how the finishing is taken, you can observe the layer by layer printing of the component, and by applying pressure, how the finishing is taking place. And you can also see the surface morphology with respect to different cycles like 50 cycle, 150 and 250 cycles, and how the final finished surface looks like, and how the before surface looks like, okay, as a 3D printed component and then finished component. And effect of every parameter is discussed. So to know the media flow direction, and also to observe the layer thickness, and as well as mainly targeting on how the finished component, okay, as built component and finished component. And the abrasive size is also proved with SEM image, like what kind of abrasive size is used, so abrasive scratch marks, deeper indentation, and if any porosity observed on the finished surface, etc. were identified. And developed media with other media. So as I said, there are two research majorly working. One is hybrid AFM. So people trying using different hybridization like magnetic field assisted or rotary or drill bit. Okay, that is one area. Second is using different types of media. Okay, so some people in the literature they used gum based media, some GUR based media, some SBR means that synthetic based rubber, okay, natural rubber, and galactominian media. Some used natural polymers, some used wax, okay, some used honeybee wax. So like that they use different types of media, and several people got patents and better results in their different media they used. And the mechanism you can see here. So the abrasive particles traveling in the work surface, and schematically whatever the observation in the SEM image, explaining what kind of machining is taken place, like rubbing action, micro plugging action, okay, and the shearing action of the abrasives. So all this we need a proof, right? So the proofs are explained with the help of SEM images. So the mechanism is explained with the help of a SEM image. So this is a possible rubbing, this is a possible rubbing action, this is a possible finishing region. So this is as built, etc. And now we are working on rotary ultrasonic. As I said, during my PhD I worked on ultrasonic assisted AFM, and in the literature we can see rotary, right? So when these two are combined, okay, when the rotary technique, rotary assistance, and also ultrasonic assistance is combined. So this is our ongoing project we are working on. Okay, the name of the project is rotary ultrasonic abrasive flow machining. So when the two effects are given, how the results. Okay, this we got under core research grant DST, and we also using ultrasonic this one acoustic emission. Okay, we are using one sensor to find out the online monitoring of the abrasive media. Means we wanted to know, we wanted to predict the surface roughness. So we wanted to know when to replace the media. or when to stop the machine, when we wanted to know the information like when we reach our required desired area, okay, something like that. We are using the sensors. So this sensor is fixed to the workpiece, and then it will continuously monitors the media flow. So there is another variant called chemo-mechanical abrasive. So we are working on this. We started to work on this. So in this particular process, the chemicals are used. Okay, so it's a combination of chemicals. So you can see here the abrasive flow machining, we are pumping to and fro, and there is a injection of oxidizing agent inside the tooling zone, and there is a heating system. So how the chemical agent, oxidizing agent we are using, and how it reacts under different temperatures, and the fixture design for that, right? And basically if you see the working principle, so the abrasive media and the substrate and the diamond film, the oxidizing agent. So how this oxidizing agent helps in finishing. So we are working on that also. So there is a lot of scope in finishing dental implants which are complex in nature, and medical implants which are complex in nature. And to see the overview of the parameters, like in the simple AFM, machine based, media based and workpiece based, whereas in hybrid AFM we have magnetic flux density and current in magnetic assisted, and shape of the rod, rotational speed in centrifugal force assisted, and drill diameter in drill bit guided, rotational speed of the workpiece in RAFF, current intensity and voltage, abrasive paste, etc. in electrochemical, and also there is a chemo FM. In UAFM, the application of vibration speed. So these are all the new parameters introduced in the field. Okay, so I would like to stop here. So in the laboratory session, you can see the setup and how it is functioning, okay, and how we prepare the media, right? So, and also 3D printing lab possible. 3D printing lab is possible to see. Shobhan? Yeah, so we can also see the 3D printing lab and as well as this abrasive flow machining lab in the today's session, okay. After lunch we have a session from Professor Vamshi, and after that this lab visits we can plan for today, okay. Mostly tomorrow 2 sessions we have, so that we will discuss, okay. So now session is open for the questions. So majorly the people from the mechanical background. So those who want to work in this area, you are welcome to discuss, not only now, later also. So you can see the laboratory arrangements, and if you want to collaborate or if you want to do some work in case of developing a new media, okay, because everyone will have different ideas. So one author tried galactominnan polymer, I tried natural polymer, some other tried rubber based polymer, like that. Some media with different properties which match our application, probably you can look into that. And mechanically also, if you want, like my project is based on rotary and ultrasonic, someone may think in a different way if you see the literature. So something like that, you can always collaborate with us. Okay. We will end this session by, okay. Thank you all. Yeah. Yes. So that's why it's not much affecting on the material. So because the abrasive media, which is with the help of thermocouple and also in the literature, it's not more than 70 degree. So that's why there is no effect on the work surface. Material properties are not going to affect because it's working under lower temperature only. The machining is taking place at lower temperature only. Still any? Still any questions? Reusability of the media, yeah. So in one of the patent, the author used a honey bee wax, and after machining, he melted the media and he has taken out the wax, removed the abrasives and reused it. So that is one climb. So reusability can be possible only if you can do this, such things, okay. Reusability is not possible for rubber milk or any other media. Now we are using silicon carbide abrasive button. Mesh size, we have 4 or 5 mesh size, okay, 120, 80, 180. Sorry? Yes, exactly, we can do that. Commonly used 180, I think, 180 mesh size. So if the abrasive mesh size increases, then the particle size decreases, right? So higher the mesh size gives better finishing, lower the mesh size gives better MRR. So we need to optimize. So optimization requirement is there. So during my study also I have optimized all the parameters. Yeah, you can think about it. We have not done that particular, but what are the results you are expecting, that is important. So we have not tried that, but if you have any idea, then no one has tried in the field. You can look into that, those things. Okay. So cryogenic helium you have seen, but AFM so far no one tried. They are doing. Probably you can see our environment, the working environment here. If you suggest something like, means, but there should be some reasoning also, like why cryogenic? Yeah. The addition of this cryogenic setup has increased the efficiency of the machine. So that we will discuss in the lab. Okay. If any possible solution is there, that we can try. Any other questions? Okay, if no questions, so we can meet at 2:30 again after lunch.